Hi everyone. I would like to welcome you back for part 2 of our discussion on section 4.1. The purpose of this video is to introduce the terms and concepts we will need in our discussion of calculus-based optimization. As we saw in the first video, optimization is the process of maximizing or minimizing some quantity. So the first terms we will introduce are classifications of minima and maxima of function. At the end of the video, we will work through an example. Normally, I would do multiple examples, but there are many videos that go through computations online. I will include some links either at the end in the slides or on Blackboard. So I'm going to jump right into this in the worst possible way, by throwing tons of words and concepts at you all at once. This is a good moment to remind you that this is a video, so you should feel free to pause and replay the video as much as you need to help you understand the concepts. The terms on this page have equivalent definitions for both maxima and minima. I will focus on the definitions for the maxima in order to save time. Just be aware that there is an equivalent definition for minima that is roughly the same. The first concept I want to focus on is the idea of an absolute maximum. I have included the formal definition here. Effectively, the absolute maximum of a function is the highest point on its graph when you restrict the graph to the domain. If that point happens at x equals c, we would say f of x has an absolute maximum at c. As we will see in the next slide, the absolute maxima look like peaks in the graph of y equals f of x. The y value at an absolute maximum is known as the maximum value of f of x on its domain. To be thorough, I will point out that the maximum value of a function is unique, but may be attained at more than one x value. For example, cosine of x attains its maximum value of 1 at an infinite number of x values. Sometimes it's not important for a point on the graph to have the largest y value on its domain. All that matters is whether the function is larger near that x value. We call such points local maxima. To help us understand these concepts, let's see what they look like on the graph of a function. Here you see the graph of a function. We will use it to qualitatively examine the various minima and maxima. Look at these 2 points. They both are the lowest points in their general vicinity. They are local minimums. This point is the highest point in its general vicinity. Thus, it's a local maximum. Notice that this local minimum seems to have the lowest y value of the entire function. This is because the function appears to go to positive infinity as x goes to either positive or negative infinity. For this reason, it is an absolute minimum. Finally, notice that this function has no absolute maximum. This encourages several questions. First, why didn't that function have an absolute maximum? Well, as we saw, the function was going to positive infinity as x went to either positive or negative infinity. As the domain was negative infinity to infinity, there is an x value that gives as large a y value as you please. The second question is, why else might a function lack an absolute maximum? Let's look at the 2 graphs at the bottom of the page. Before we move on, this is a great moment to mention that for various reasons, we may want to restrict the domain of our function when discussing maxima or minima. A real-life example of this is if you're driving to your friend's house at 2 p.m., you don't need to consider traffic at 7 a.m. Well, unless your friend lives 17 hours away. So let's turn our attention to these graphs. Both lack an absolute maxima for what appears to be different reasons. We'll see in the next video that it actually happens for the exact same reason. The first graph is the graph of y equals 1 over x. We know that it has a vertical asymptote at x equals 0, and 1 over x goes to infinity as x goes to 0 from the right. So for the same reason as our previous example, there cannot be an absolute maximum. The second graph lacks an absolute maximum for what is a rather annoying reason. It feels like x equals 3 should be the absolute maximum, but it just isn't in the domain. Hence, no absolute maximum. I will point out before moving on that both of these domains lack endpoints, which will be a major concept in the next video. Let's turn our attention to where max and mins can even occur. First, you notice that in the case of y equals x, if we had included the endpoints 0 and 3, suddenly we would have had an absolute maximum and minimum. In what other situations can an absolute maximum occur? So let's imagine that our absolute maximum does not occur at an endpoint. Then it would look like one of the two graphs shown here. Notice that both functions have a local maximum at x equals 0. But what else do they have in common? Well, both functions are increasing for negative x and decreasing for positive x. I will note here that there is a third possibility not pictured here. If our function was instead a constant function, whose graph is a horizontal line, it would have an absolute maximum and absolute minimum at all values of x. So what does this mean about the derivative of these functions? Since f is increasing when x is negative, we see that f prime must be positive for negative x. Similarly, when x is positive, f prime must be negative. There are only two ways for the derivative to go from positive to negative. Either it goes through 0 at x equals 0, like in the graph on the right, or it just does not exist at x equals 0, like in the graph on the left. These two behaviors are so important that we give them their own name. If we have a function continuous on an interval, a critical point or critical number of that function is a value in that interval such that either the derivative is 0 or the derivative doesn't exist. Critical points will play a central role in our study of optimization. Let's take a moment now to compute the critical points of a specific function. I recommend all of you pause the video here and attempt to do this on your own. I've included the definition of critical points on this slide to help you out. So now that you've had an opportunity to try this problem yourself, let's work on it together. It may be helpful to remember that the cube root of a quantity is the same as that quantity raised to the 1/3. Since critical points have to do with the derivative of f, the first thing we'll do is compute f prime. In order to compute f prime, we will need to use both the power rule and the chain rule. So first, the power rule tells us the derivative of the outside function should be 1/3 times the inside function to the negative 2/3 power. All this should be multiplied by the derivative of the inside, which is 2x minus 1. We can rewrite this in the following way. We know that there are two kinds of critical points. The first happens when f prime is equal to 0. The second happens when f prime does not exist. So when is f prime equal to 0? F prime should be 0 when the numerator is equal to 0. So 2x minus 1 has to be 0. There's only one x value at which this happens, and that is when x is equal to 1/2. The second kind of critical point occurs when f prime fails to exist. In this case, that'll occur when the denominator is equal to 0. That happens when x squared minus x equals 0. Factoring, we see that x must be either equal to 1 or 0. Putting all our work together, we see that the critical points are at x equals 0, 1/2, and 1. Alright, that's it for this video. Tune in next time for the exciting conclusion of section 4.1.